if we go back through kind of the steps that we solved when we looked at solving example 1, and when we set up reduction of order in the first place, then one of the things we can kind of handle is, let's suppose that we put our second order differential equation in standard form, meaning that we don't want to have a coefficient function in front of y double prime. If you had something in front of there, like in form 1, where you have like an a2 of x times y double prime, simply divide the entire equation by a2 to clear it off and put it in this form here. Again, if we knew a solution, so if you had a solution to the second order differential equation, let's call it y1, you could do the exact same thing and solve this in general. We would again suppose that y equals to u times y prime. We would want to go ahead and form y prime and y double prime and substitute them into this differential equation. To find y prime, you would have a product rule. It would be u prime times y1 plus u times y1 prime, like this. Take the second derivative, you would need to do two product rules. The derivative of this would be u y1 double prime plus you would have a u prime y1 prime. The derivative of this one would be a y1 prime u prime plus y1 u double prime, and you would have two common terms you can combine to get a 2y1 prime u prime. We take these expressions along with the original function and plug them into this differential equation, and if we rearrange things, what you would get would be, we would have a y1 u double prime term plus a 2y1 prime plus py1 times u prime. But then the last term, which would be over here, which would be something times u, is going to be u with y1 double prime plus py1 prime plus qy1. Now recall that y1 was one solution to this differential equation, which means that if you plug this in, so if you replaced y with y1, then that expression would be equal to 0. And so this coefficient here is going to be 0, and so this term drops out, and we're simply left with y1 u double prime plus 2y1 prime plus py1 times u prime equals to 0. We can go ahead and make the same substitution we did a moment ago. For the reduction of order, we're going to let w equal to u prime, and then that means that w prime will be equal to u double prime. We can substitute that in, and we would get now this first order differential equation in the variable w. We can solve this. It's both linear and separable, so you can separate and integrate. I personally, when I derive this in class, would typically do integrating factor, but you can do it like this too. We would solve first for w. You integrate the left-hand side. It's going to be, as an integrating factor, you're going to get w times y1 squared is equal to negative p dx. We solve this for w. We would get that w is equal to c1 e to the negative p dx divided by y12, and then because y was equal to u prime, you have to integrate that whole thing one more time, and this is what we would get. Our u is going to be equal to some constant integration times the integral of e to the negative p dx divided by y1 squared dx. That whole part's all in the integral, plus some constant integration c2. In order to kind of simplify this and make things as easy as possible and not to have to fuss with coefficients, if we let c1 be equal to 1 and c2 be equal to 0, then we get that this would be our term for w, for u, and then our second linearly independent solution would be y equals u times y1. Okay. So this form here, if you want to remember this, you certainly can, or if you want to take notes on it. It's kind of helpful that it kind of skips through a lot of the intermediary calculus and algebra needed to solve for y2. I remember when I was first kind of learning this material, I didn't feel like memorizing this formula, and so I would go through these steps above in that derivation every single time in order to solve these types of second order ODEs. The more pragmatic I get, I realize that this is just kind of reduces it to a computation. The long and short of it is I would like you all to understand how reduction of order works, the manner in which we're able to do the substitution, Yet at the same time, if you're asked for a second linearly independent solution, you may use this formula to work them out. Okay? Let's do one of these together. So let's suppose that we know that y1 equals x squared is a solution of x squared y double prime minus 3xy prime plus 4y equals 0, and we're asked to find the general solution on the interval 0 to infinity. Well, we do have one solution. From what we found a moment ago, we know that a second solution will be of the form y2 equals y1 times the integral of e to the negative integral of p of x dx divided by y1 squared dx. But now be a little bit careful here. We're not ready to solve for p of x or to describe p of x because this is not in standard form. We should begin by clearing off that coefficient function from the second derivative, divide everything by x squared so that we have y double prime minus 3 over x y prime plus 4 over x squared y equals to 0. So we have to write it like this first. We now see that p of x here, p of x is equal to the negative 3 over x, that's the coefficient function for y prime. So our second solution should be found by doing the following. It's going to be y2 equals, we need y1, well that's going to be x squared times the integral of e to the negative integral of p of x, that's going to be negative 3 over x dx divided by y1 squared, that's going to be x squared dx. This is going to be equal to x squared times the integral. We would have to do the antiderivative in the numerator first. So have x to the fourth on the bottom dx. For this piece here, this is going to be e, the negative and the negative will make a positive. I can pull the 3 out. You would get 1 over x dx. We know that that's going to integrate to a natural log. So we have the x squared times the antiderivative of e to the 3 times the natural log of x, all divided by x to the fourth dx. This is x squared times the integral. Bring the power in. So it's e to the ln of x cubed over x to the fourth dx. This is going to be x squared times the integral. We know that the e and the ln cancel, so we get x cubed divided by x to the fourth. This is going to be x squared times the antiderivative of 1 over x dx, and that in itself will be x squared times the natural log of x. And I'm not going to put the constant part with that. So what we end up having is the following. The general solution should be found by taking our particular solutions, our y1 times some constant, plus c2 times our second solution, y2. So the general solution is going to be the following. It's going to be c1 times, which is x squared, plus we're going to have c2 times x squared, the natural log of x.